Hi there. In the course of this video, we're going to look at what is the expectation of discrete random variables. Thus far, in this video series, we have looked at two types of discrete random variables. I've done one video specifically on the binomial random distribution and also a video on the Poisson distribution. Both of these are discrete random variables, and in the videos on these two, I have explained what they are, how they're derived, and also how they're used. So I encourage you to go and watch these if you are uncertain of these details. Throughout the course of this video in particular, what we're going to do is to determine the expectation of these distributions. But before that, let's first understand what do we mean when we say expectation to begin with. So when we use the word expectation, what we're actually asking is for the expected value of a discrete random variable or some kind of discrete distribution. So that is the expected value. So expected value, we can understand that as meaning the weighted average of all possible outcomes, of a certain random variable or distribution. So when we say weighted average, what we then mean is the value that you can expect to get if a certain process, that's a random process, is repeated a large number of times. So when we speak about a random process and a random variable, you can look at the first video in this video series and you can see that we explained that we can designate a random variable by capital letter X, and with this kind of variable we would have different probabilities that would be associated for whatever outcome results from a random process. So this capital letter X will take on a certain value from a set of values that's small letter xi. And a popular illustration of this is, for example, if you toss a coin 5 times, then how many heads would you get? You can designate how many heads you would get as a random variable. And in this case here, small letter xi will take on values between 0 and 5. So it'll go 0, 1, 2, 3, 4, and 5. So the question here that we're asking when we talk about expected value is how many heads should we expect to see if we flip the coin a large number of times? So we think of the probabilities as weights. And when we say weights, what we're saying is the probabilities give more importance to more likely outcomes. So perhaps a simple way to illustrate the concept of expectation or expected value is to look at a simple game of dice in which we roll dice and win some money based on what we roll. For example, if we roll the dice and we get a 1, then it means that we get $1. If we roll a 2, then we get $2, and so on. And of course, we can roll a maximum of 6, and the maximum we'll get is $6. So let's just say we roll the dice a large number of times. If we successively roll it a large number of times, the question is, what is the average amount we will win? So the average amount that we win corresponds to the expected value or the expectation. And how would we determine this? Well, if we think about the probability, each outcome of the dice has a likelihood of 1 over 6. Since there are 6 options in total, and if we roll the dice, we can only get 1 of that 6. So how do we determine the expectation? So the expectation of this particular random variable, we write it as capital letter E and we show the X in square brackets, and we roll a 1, and that has a probability 1 over 6. And then we get $2, and that has a probability of 1 over 6. And then 3 also has a probability of 1 over 6. And the same with 4 and 5 and 6. So to determine the expectation, all we do is we multiply our outcome, that's 1, 2, 3, 4, 5, 6, by the probability of each outcome, and we add it up all together. And if we do this calculation, then we find that the expected value or expectation is 3.5. So this is not a possible outcome if we actually roll the dice. We can't get 3.5 if we roll the dice. We can only get, a single integer between 1 and 6. So what this means is that the expected value doesn't necessarily mean that it's going to correspond to one of the outcomes. What it does actually mean is that if you play dice forever, for a very long time, on average, per roll of the dice, you will get $3.5. From this, what we can do is, in general, define what the formula is or what is the equation for expectation of a discrete random variable. And we can see from this example that the expectation of the random variable x is actually the sum of firstly the outcome xi, in this case here 1, 2, 3, 4, 5 and 6 were the outcomes of rolling the dice. And what we did is we multiplied it by the probability of the random variable capital X taking on each of the values in the set that's designated by small letter xi. What we're going to do now is determine the expectation of the binomial random distribution. You would recollect that the probability of the binomial random distribution, in which the random variable x takes on a certain outcome that's designated by the letter k, and k is a number and it goes between 0 and n. The first term is n choose k, and this is multiplied by p. This is small letter p to the power k, and the small letter p is the probability of each individual outcome k. And then this is all multiplied by 1 minus p to the power n minus k. I advise that you go and rewatch or watch the video on the binomial random distribution to understand how this equation comes about. So to determine the expectation of a certain random variable x, we just saw now that what we have to do is multiply this probability distribution by the outcome k, or what is designated by the outcome, in this case it's k, and then we have to sum it up. So we do the same for the right hand side. We'll multiply this by k and we will sum it up. And k here, as I said earlier, goes between 0 and n. So now, to derive a general result for the expectation, all we do is simplify this expression on the right hand side. And we do that firstly by expanding out this definition of n choose k. So we're going to have k, and the definition of n choose k is n factorial, and then we're going to divide that by n minus k factorial multiplied by k factorial. And this is all multiplied by p to the power k and 1 minus p to the power n minus k. And we also have to remember that all of this is being summed. So what we can do is now simplify this expression by cancelling out some of the terms. And we can do that by firstly seeing that k factorial is actually k times n k minus 1 factorial. Then the k's will cancel out in the numerator and the denominator. The second thing that we can do is we can also do the same thing for n factorial. So n factorial can be written as n into n minus 1 factorial. So we can pull that n out. So let's do that. So we have n multiplied by this big sum, and this k's have gone. So what we're left with is n minus 1 factorial. That's this expression of this term. And then this is divided by n minus k factorial, that part, and k minus 1 factorial. And of course, this is multiplied by p to the power k and 1 minus p to the power n minus k. Now, what we also can do is we can separate this p to the power k, and we can write it as p into p to the k minus 1. All we just have done is we have split these exponents. And then we can take this single p and bring it out of the sum. So in front of the summation, we will have n times p. So what we do next is just simplify this term within the summation. And how we're going to do it is by making a substitution. So this k minus 1, what we're going to do is we're going to substitute I instead of k minus 1. So the next step is to substitute I is equal to k minus 1. Doing that, we're still going to have np, and then now we have this sum. So this n minus 1 factorial in the numerator remains as is. And then this is divided by, now substituting in I is equal to k minus 1, what we're going to have is n minus 1 minus I. This is factorial. So instead of k, we took k to the 1 to the other side, and we got I plus 1 is equal to k, and then that's how we get minus 1 minus I. And then k minus 1, that's just I, so we'll have I factorial. Then we have p to the k minus 1, so that becomes p to the power I. And then we have 1 minus p, and this is to the power n minus k. So in the same way we did this particular term, all we'll have is n minus 1 minus I. We now further simplify this term. So we have n times p, and this n minus 1 factorial divided by this denominator, it can simply be written as n minus 1 choose I. And then we have p to the power I times 1 minus p to the power n minus 1 minus I. The next step is to realize that we can further simplify the term within the summation by using the binomial distribution. If you'd recall the binomial theorem, it is a plus b to the power n is equal to the summation, where we have some I going from 0 all the way to n, and then we have n choose I. Then we have a to the power I times b to the n minus I. So this term within the summation is actually the binomial theorem. However, instead of n, of just n, we have n minus 1. So we can rewrite this step as n times p, and then we have p plus 1 minus p all to the power n minus 1. So it's a direct analogy. So this a plus b is like p plus 1 minus p. So we have a here instead of p, and 1 minus p instead of b. And instead of n, we have n minus 1. So this n becomes n minus 1. So this can be simplified quite nicely by recognizing that p plus 1 minus p is just 1. So this entire term within the square brackets is just 1. So that p and that p become 0, and we're just left with 1. So this means that this entire expression just becomes n times p. So what this says is that the expectation of a binomial random variable, or the binomial random distribution, is just n times p. So what we're going to look at now is determining the expectation of the Poisson distribution. And you would recall how it's defined, or how it was derived, as lambda to the k divided by k factorial multiplied by e to the minus lambda. And you would remember that lambda was equal to n times p. So please go and watch the previous video on the Poisson distribution to understand how this particular equation is derived. So as we have just seen now, we determine the expectation of the random variable by taking this probability distribution and multiplying it by each of the outcomes. In this case it's k, and then we sum it, where k will go from 0, and in the case of the Poisson distribution, it can go up all the way to infinity. So we do the same with the right hand side. So we have k, and now we sum between 0 and infinity. So that's actually k is equal to 0 and to infinity. We can now proceed to do some mathematical trickery to simplify this. So this k factorial, we can actually write that as k times k minus 1 factorial. In that case, these k's will cancel out in the numerator and the denominator. However, what that does is it has an effect on where k starts from. So now k won't start from 0, it'll actually start from 1, because we can't have the negative number as a factorial. So what we can also do is we can take this e to the minus lambda out of this summation. That doesn't affect anything. And we can also then split this lambda to the power k. So let's do that. So we'll take out this e to the minus lambda from this equation. We have e to the minus lambda. And then now this is multiplied by this summation, where k now starts from 1 and goes to infinity. And then we have lambda times lambda to the k minus 1. So since lambda is on its own, we can also just bring that out of this summation. We can just write it in front. So let's write it here. So we have lambda. And what's left? We have k minus 1 factorial. And that's about it. So we can do a substitution at this point. And what we can do, as was the case with the binomial random distribution in the previous example, we can just substitute. We can substitute that I is equal to k minus 1. So what that means is that we'll have lambda times e to the minus lambda times this summation, where k will go from 1 to infinity. And then we'll have lambda to the power I. And this is divided now by I factorial. So you would also recall from first year maths or high school maths or something like that, that this summation term is actually a very simple identity, and we can make use of that identity. This summation is simply just e to the power lambda. So I would suggest that you just consult your calculus notes from first year to understand how that is the case. So this summation of lambda to the power I divided by I factorial, that is just e to the power lambda. And then we have e to the minus lambda that's left, multiplied by lambda. We can see that this minus lambda and this lambda, it's just going to give us e to the power 0 which is just equal to 1. So what this means is that we are just left with lambda. So the expectation of the Poisson distribution, all it is just lambda. So what this means is if a random process follows the Poisson distribution, the long-term average value is simply just lambda. So in the course of this video, what we have done is we have shown how expectation comes about. We have explained conceptually what it is, and then we have shown mathematically what is the expectation of the binomial random distribution and thereafter the Poisson random distribution. Thank you very much for watching.